but I think we can get started now. All right, so before we start, just want to, of course, thank Jeremy for taking the time to share his work with us. Really appreciate it. And I'd like to thank Bing for helping to organize and co-host this event. So a little bit about Jeremy. He's a PhD candidate advised by Jerry Zhu at the University of Wisconsin-Madison, and also an NSF League Fellow. Before that, he got his bachelor's in math and computer science at UIUC and a master's at UW-Madison as well. And Jeremy's research focuses on efficient approximability of combinatorial and multi-agent optimization problems under constraints, with published work at NeurIPS, ICML, RLC, among others. And his ultimate goal is to develop algorithms with provable guarantees and complex scenarios that reflect the real world. And we're excited to hear more about that today, of course. So with that, Jeremy, the floor is yours.
Yeah, thanks, Ryan, for the introduction. And of course, thank you for allowing me to talk. Today, this work's going to be kind of a nice mix of some theory and some reinforcement learning. So if you're a theory person, I'm sure you'll enjoy all the techniques. If you're an RL person, I hope you enjoy the results. And also let me know if anyone has questions. So the title here is not the title of the actual paper that was presented at NeurIPS, but a flashier title to really give you the idea here. Because my philosophy is that essentially constrained reinforcement learning is more like the knapsack problem than maybe more standard reinforcement learning. And we're going to go a little more in depth on that. So to start us off, I have this funny example that I came up with using a generative model. It's this Smithsonian bandits. So if you imagine, the famous Smithsonian Museum, and imagine some bandits are trying to steal these rare artifacts from the museum. And I like to think of this as like the knapsack problem. So you could have these old ancient artifacts, and then your robber has some knapsack or bag that it can use to, take things. And maybe it takes the ring and the crown, and then, well, that filled up the whole bag. So now you have no room for the painting on the wall. So this is like the standard knapsack problem. You can also view it as this integer optimization, where your goal is to choose these xi's, which represent whether I'm going to take the ith item or not. If you do take the ith item, you get a value vi. And if you don't take, and if you also take it, you also incur a weight of wi on your total knapsack. And then you have a budget, which is essentially how much that knapsack can hold before it's going to burst. So naturally, you want to maximize the total value of items subject to they all fit in your bag. So this is the standard knapsack. I'm sure we're all familiar with it. And now I'm going to keep adding layers of complexity. So the first layer, realistically, is, okay, if you're in a museum, you can't just arbitrarily decide what to pick. There's kind of this online sense of you view things in order. So the robber enters and immediately, you could think of if it's just a big gallery of items, he has to make his decision from left to right. And he doesn't really have time to go back and try all possible combinations because, he tripped alarms and the police are coming. So he really only has time to go through each of these items once. And so he has to decide immediately, essentially, what he's going to take and what he's not going to take. So already you're seeing kind of there's this online decision-making aspect. Okay, let me make it even harder. So let's say, well, in the ideal version of knapsack, you know how much everything weighs. But if you're just in the Smithsonian, you can only really eyeball it. So you see this crown, kind of looks like it might be 4 pounds, maybe, but there's a margin of error. It could actually be a little heavier or a little lighter than you expect. And so this is a problem because what if you choose to take the crown, but it ends up being heavier than you thought, and boom, your bag is broken and the police have got you. So naturally, when you have these stochastic variants of these problems, well, the question is, what does the problem even mean anymore? So for example, you could just say, I'm happy with, on average, the bag won't burst. Or maybe you're a little more of less of a risk taker and you're like, okay, I want the bag to be safe 95% of the time. Maybe you're really stubborn and you're like, every single time, no matter what happens, I need this bag to be safe. So you're being very conservative with your choices. And each of these models of constraint will lead to a different version of the problem, and oftentimes with different computational complexities. So in this talk, we're going to consider all three actually. But for now, I just wanted to kind of give you a taste of the form these things take. So also because there's randomness, our X choices are no longer just a 0 or 1 variable. They can now be functions that adapt to what's been seen so far. So if we have a budget of 15, you could imagine this giant tree where we decide deterministically we're always taking the first item, and then we get some realization of the weights. And say in one scenario where the weight's very much less than we expected, well, then we can take the second item. So if the first item's light, it's safe to take the second item. But in the scenario where the item took up the entire bag, well, now you're forced to never take the second item. And similarly, under other branches of this tree, you might make different decisions. So now instead of just X being a vector of zeros and ones, you should now think of it as this giant tree based on the full history of things we've seen so far. And so I hope now, if you're familiar with RL, you're kind of hearing, oh, history, decisions, adapting, there's a connection between these things. So let me make the problem even harder. Now we're going to add context. So it's not just as simple as there's a single hallway with all the good items you want to steal. There's different rooms, and the bandit has to also think about, if I choose this room, maybe I get not as good items, but that leads me to another room with very good items. So now there's this entire graph you have to consider that constrains the decisions you make. And I'm just going to think of this as a general context. Whatever that might mean would depend on the application. And so now our decisions are going to be also a function of the context. So what items we take depend on which room we're in, or which rooms we want to go in the future as well. So yeah, so we start with the knapsack problem, and now we've added a bunch of different layers, and kind of the final model for all of this is going to be a constrained MDP. And I claim this captures all of these different complexities from the bandit example. So let me briefly go over what a constrained MDP is for anyone who maybe is less familiar. It's this model of sequential decision making where you could think of you have some autonomous agent or a robot or a person, and they're going to interact with some environment, some world, some system. So that's the robot and then the little globe down there. So here the environment, which is the little globe, has some state or context, essentially some information about the world that you would need to make decisions. So the world's going to tell you its information, summarized by the state. The robot's then going to take an action. It's going to somehow interact with that world based on the information. So we usually think of this as some function of the state, which is the little pi there. And then once the robot takes an action that affects the world, and then so a few things will happen. You'll get a reward or maybe a cost, and then the state of the world will change. And this will continue a total of some h times, where h is some finite horizon. So in the knapsack example, you could think of the state as simply being which item we're on, item I. The action is just the 0-1 decision of whether we take it or not. And then our reward will be either the value if we decide to take it, or 0 if we decide to leave it alone. And similarly, the cost is either the weight or 0. So this is the idea. Formally, there's this complicated thing called an MDP. So if you're not super familiar with it, it's basically like a finite state automaton where you have these nodes that are states, actions lead you to different states, and you have this graph telling you where actions go, as well as the rewards. So in general, these are described by a set of states, a set of actions, a reward function, some cost function, and transition probabilities. You also have the total time that you're going to repeatedly interact with the system. So for example, let's say h is equal to 3. So real quick, let me go into more depth of what these things are. So here, these little a's here, these are the actions available, such as take an item or not. The s's here, of course, are the states. The first thing in these little sets here, that's the reward. So it's saying if I took action A12 in state S1, I will get a reward of 10. And the 1 is the transition probability. So it says if I take action A12, I'm guaranteed to take this arrow to S2. On the other hand, if we were in S1 and we took action A11, there's a half probability chance we actually stay here, and there's a half probability chance we go to S2. So this is kind of the stochastic aspect of the MDP model, is that when you take an action, it might change the state, it might not. It might change the state in some ways you'd want, it might change it in some ways you don't. There's this essence of randomness there that we have to manage. So in the knapsack example, this is basically saying maybe you thought you were going to go to a room when you took a door, and it took you to a different room you weren't expecting. And that's something the bandit has to take into account if it's going to make it out before the police get there. All right, so how does an agent actually interact with these environments? Well, using these things called policies. And the policy, which was the little pie from before, is just usually a function from states to actions, saying, given my information, what action should I do? So for our example of this MDP, you could say, okay, in state S1, I'm always going to take A12. This is kind of a good idea because you're always going to get that reward of 10, which is a very big reward. And then in state S2, well, there's only one action we can take, which is A21, so we're always going to take that action when we're there. And then the way we measure how good a policy is with this thing called value, which generally in most applications is just the expected total reward we get from interaction. So for this specific MDP, the value is going to be as follows. Let's just say we start in state S1. We're going to take that action A12. So that's going to immediately give us a reward of 10. And then it'll transition us into S2. So now the world's in state S2. The agent learns that it's going to follow its policy and take action A21, gets a reward of -1. We take the self loop, so we're again back in S2. We do the same thing again. And in total, our expected return will be 8. We get 10 at the first step and then -1 in each following steps. So any questions on this model of MDPs? Because we're going to use this as kind of the fundamental thing we mess around with in this talk.
Feel free to unmute or just put it in the chat if you want me to read it out. I had a quick question, kind of far back, but why is the one constraint called almost sure instead of like completely sure? Because it looked like it was probability equal to 1.
Yeah, so this is just a technical term from probability theory.
Mhm.
They use almost sure. That's like a technical term for with probability 1.
Okay, gotcha.
Why they call it that, I don't know. I think the idea is just that even in a probability 1 event, there could be measure 0 sets that don't obey the constraint. So I guess it's just to be precise.
Fair enough.
But yeah, good question.
All right, seems like we can keep going.
Cool. So that was the basic RL/MDP setup, and now we're going to add constraints to it. So that's the little cost function C I mentioned before. So a super easy example is, let's say you have a self-driving car, you want to create a route from Madison, Wisconsin to Milwaukee. because I'm in Wisconsin right now. And naturally, the first thing you're probably thinking is, oh, I want to minimize my time, right? So an hour, 24 minutes, that's kind of the main thing you care about. But there's other things we care about, like your fuel. It doesn't really matter how short the route is in time if you run out of fuel and don't even make it there. So the amount of gas you're consuming is a really important aspect to consider. There's also other concerns like how much CO2 you're consuming. Maybe there's routes that are more efficient in terms of the environment, and you could think of wear and tear as well. Maybe there's a super fast route that just has horrible roads that will destroy your wheels, and then you have to keep getting maintenance on your car. So there's a lot of different objectives we care about besides this obvious one of time. And constrained RL will allow us to handle all these different aspects by using appropriate constraints. So mainly like for gas, if your cost corresponds to gas consumption, you just want your total cost to be at most your gas tank's size to make sure you never run out of gas. So in this talk in particular, I'm going to focus on deterministic policies. So we saw before pi is a function mapping S to some action, but in general, it could actually be a distribution. It could say in state S, I choose action 1 with 50% probability, action 2 with 50%, or some other general distribution. But I would claim that deterministic policies are usually preferred. Some reasons for that are they're cheaper. You don't have to worry about, simulating some complex random coin flip while you're executing the policy. You don't have to store all these probabilities. It's just more efficient in general to have a deterministic policy. These are better for multi-agent settings because if you have two self-driving cars communicating and they're making random decisions, that's going to be kind of hard to avoid collisions. You really want certainty when you're dealing with multiple agents in the system. They're also more trustworthy. Now, what do I mean by this? Well, imagine you had a doctor who was flipping a coin to decide what treatment to give you. Even if, statistically those treatments are equally good, as a patient, you're probably not going to really like that. It's probably going to give you some anxiety. And formally, we call this predictability or reproducibility in machine learning, which is just the idea that if you run the same policy many times, you're always going to essentially get the same outcomes. And so we really like that because if you imagine an industry application or any application where safety is of concern, we really want these policies to be very consistent with what they do so we know what to expect. Whereas for a stochastic policy, of course, it could just randomly lane change. And even though that's legal and maybe even safe, if you saw someone just lane changing back and forth, it'd probably make you not feel very great. And the last reason why this is great is deterministic policies are actually optimal for some of the stronger constraints in the literature. And so we'll talk more about that in the very next slide. So what are the constraints people consider? Most of them are just identical to what I mentioned before. So you could just take the average cost and say that's good enough. That's what was classically done for many years at the very beginning of constrained reinforcement learning. But very quickly, people realized this is a bad idea because you could have a huge chance of making really unsafe decisions. So then chance constraints were introduced. They're a little safer. So instead of arbitrarily large probabilities of making bad decisions, you have some fixed delta, like 5%, which is um, your allowable range for violation of the constraint. Now there's a stronger one, almost sure. This again, just as before, this is just probability 100%. You are good. And now there's actually one extra one when we talk about RL, which are called anytime constraints. So the difference between almost sure and anytime constraints are the probability one guarantee has to hold at every point in time. So the weird thing about almost sure constraints, say in the self-driving car example, is it's okay if you run out of gas as long as at the end of the process you have gas. But if you run out of gas, the process ends anyway. So it's kind of something that makes sense in theory, but in practice doesn't really make sense. Whereas the anytime constraint says at any point in time, we can never run out of gas, and that makes sure the process actually keeps going. So that's the differentiation there. Now, the cool thing about all these constraints is you can model them simply just as a cost function. So for expectation constraints, you can define the cost function as the expected total cost naturally. For chance constraints, you can view this cost as the probability of violation. Almost sure this is just the worst case costs over any possible realization of your tree of possibilities. And then any time is almost the same thing, except you have an additional maximization over individual time steps. So I would think of almost sure constraints as a constraint on the leaves of your tree, whereas an anytime constraint is a constraint on every single node in the tree. That's kind of the difference there. But I'll say, if you're not super comfortable with any of these, it doesn't really matter because we're just going to abstract it as a general cost function. And we can actually handle all of those different cost functions, other than the almost chance constrained one, which we'll talk about a little later. It's because they're provably unsolvable anyway. So the main problem we want to consider in this talk, finally halfway through, is we want to find a policy that's deterministic, satisfies the constraint, and maximizes our total reward. So we want all of these things to be true at once. And here the C is a general cost criteria. It's a general cost function like we saw in the previous slide. So our goal is maximize reward, but also taking into account that our total cost is at most the budget. So I hope it's easy to see that this is like almost exactly the knapsack problem, just with some subtleties. If you just replace the reward with V, that's total value, replace the cost function with the total weight, and then you immediately get the original knapsack problem. So now the question is, can we compute near optimal deterministic policies efficiently? And by efficiently, I mean in polynomial time. So I'll just tell you right now, the answer is usually not. Like the problem's NP hard to solve. That's just with one constraint. If you add more than one constraint, even just finding a feasible policy, one that obeys all the constraints, is NP hard. And so since feasibility is NP hard, of course you can't even approximate it, the value at all. You're going to get something with arbitrarily bad value. Even worse, if you have a lot of constraints, you can't even find a policy that even close to satisfies the constraints. So you might say, okay, maybe I can't get my total cost to be at most the budget exactly, but maybe I could get it to be the budget plus 10 or something. Not even the case if you have too many constraints. So the problem really scales with this number of constraints. It gets much harder as you increase the number of constraints. So also the problem is not continuous. This might be kind of obvious if you're very familiar with combinatorial optimization. But if you're coming from more of an RL background, the standard way to solve most problems is you set up some gradient descent method and, use continuity of the value functions to solve it. But the constraints here actually break all these continuity assumptions. So standard RL methods won't really work. Even standard dynamic programming won't even work. And this is just because essentially the subproblems you would want to solve have dependencies on both the past and the future subproblems. So if you think of that example where you're in the museum, the Smithsonian, which items you pick now and which room you go to next depends also on the future rooms you want to go to. So that makes it more complicated because normal dynamic programming, you really want to summarize the past and use that to help you with the future. But there you need to know both the past and the future. So it's like there's just nothing you can really do using standard dynamic programming. Now, I want to emphasize it's standard because we will end up using dynamic programming just in a very, maybe a little counterintuitive way in a second here. So these are the challenges. Mainly the NP hardness is the big problem here. So, okay, if all these things are so hard, can we actually answer this question in any way that's positive? Surprisingly to me, the answer is yes. And in fact, not only can you approximate these things, you can get an FPTAS, which is like the best possible approximation guarantee you could hope for. So formally, what we're going to design in this talk is both an additive and relative FPTAS. And these will include a general class of costs that cover both expectation, almost sure, and anytime constraints. All right. So this is the ultimate goal through the rest of this talk is to build this FPTAS. And if you're not familiar with FPTASs, the idea is I'm going to give you an epsilon, which is my approximation error. And then your job is to give me a policy whose value is only epsilon away from optimal. So either the optimal V star minus epsilon or V star times 1 minus epsilon, depending if you want an additive or relative guarantee. And of course, you have to do this in polynomial time in both the input size and in 1 over epsilon. You don't want to be, you don't want to take lots of time in terms of the error as well. So like I said before, we can't do chance constraints, but these are provably inapproximable. Even just computing a feasible policy for a single chance constraint is known to be NP hard, which to me is kind of counterintuitive because, you have expectation constraints are the easiest. If we didn't care about deterministic policies, those are actually solvable in polynomial time. It's the deterministic part that makes the problem hard. And then for almost sure constraints, it's actually known that you can approximate, at least feasibility wise, to some extent, when you have one constraint. But once you go to the middle one, chance constraints, which you think it gets harder as you go down, but for some reason the middle one's the hardest. You just can't do anything for that one. So it's kind of a weird little subtlety there with the complexity. Anyway, so our goal for the rest of the talk is to build this FPTAS. So how are we going to do it? So I'm going to claim the key insight here to solve or overcome this feasibility bottleneck is efficiency policy evaluation. So what do I mean by policy evaluation? In general, that just means you can compute the cost of a policy efficiently. So I don't need you to necessarily optimize it, but I should be able to, if I give you a policy, you can tell me how much it costs. Which of course, if you can't do that, we can't solve anything. So it's very simple assumption. It's not too crazy. So I'm going to take that intuition and just unpack it a little bit. So in particular, we want to satisfy the specific recursive notion of policy evaluation. So if you're familiar with RL, there's this well-known thing called the Bellman equation, which says the total value of your policy can be computed recursively as a function of its future values. So I'm calling that time recursive. You're recursively computing this function over time, the time horizon. So you could do the same thing for a cost function. I mean, there's not really a huge difference there. The weird thing is the space recursive. So not only should you recursively compute this over time, I want to also be able to decompose it over the state space. So that might be a little abstract. I'm going to flash at you for a second what this means formally. It's a little weird. So I just want to point out, skipped it by accident. So I just want to point out here, this is the time part. So this is kind of just a overcomplication of the normal policy evaluation equations. It just says my current cost, little h, can be computed as a function of my future cost, h plus 1. So it's written in a crazy way, but this is kind of standard. But what I also want to be able to do is then break down this equation into an additional function over states. So if little t is a state, I want to say that somehow this f function here breaks down into our future state, and then we're doing some kind of binary operation to it. So don't focus too much on the specifics here, just keep in your mind we're recursively computing things both throughout time and then across space as well. And we'll get to see this in more depth in a second. So that's the key property we're going to need for our results. And now the fundamental idea here is we're going to convert this problem we care about, maximize value subject to a cost constraint, into its reverse objective. So minimize cost subject to a value constraint. And I hope it's easy to see that these are going to be identical. So the minimum cost you could get that gets you a large enough value, those policies will be exactly the optimal policies for the original problem because they get optimal value and they have minimum cost, so they'll be at most B. So this is the key thing we're going to use. And now how are we going to exploit this? Well, we're going to take some inspiration from Knapsack dynamic programming approaches. So if you're familiar with this DP here, all we're doing is saying if we're at item I and we've accumulated a total weight so that we only have a budget of little b left in our knapsack, then to optimize the knapsack right now, we just try both options of taking the item, we get value vi, and then in the future, we have wi weight less than we used to. Or we can ignore this item and then just keep going on with our current budget. So this is the standard way you would solve the knapsack problem in your intro to algos class. But what you might not know is there's actually an alternative version of this based on a demand. So here the idea is kind of swapped. So instead of maximizing our value and our budget keeps going down, here we're going to try to keep our cost low and have a total demand on how much value we need to get. So here we're going to say, what's the best cost that gets a total value of at least D? Well, that's going to be, if we take it, we accumulate an additional weight of Wi, but we reduce our demand by Vi. We need fewer total value to achieve the objective or achieve the constraint. Or we can again ignore it, and then in the future we have to accumulate a total demand of D still. But we don't incur any weight, so that's the nice thing. And these are both equally good ways to solve the knapsack problem, but the demand version is a little nicer because it's easier to then round the inputs to this K function, and that will give you a nice approximation algorithm. So if you're familiar with the FPTAS for knapsack, it basically boils down to rounding all the values and then solving this DP. And we're going to essentially do the same thing for our constrained RL problem. So here what we're going to do is, again, basically have a demand, and we're going to add that to our state space. So instead of our state space just being S, you want to think of it as S comma a little v. And the idea here is we need to choose these v's so that our total expected value will be this v. So we want that the optimal value at this state and value demand is exactly the minimum cost of any policy that gets you a total value of little v. So that's just kind of reflecting the recursive structure of the original knapsack problem. Okay, so the value demand idea is not too crazy, but how do we actually implement this? So this is what we want to happen. We want to be able to have these little v's being our demands. So the idea here is, how are we going to choose the little v's? Well, we're just going to try all of them in standard dynamic programming fashion. And when I say try all of them, I formally mean we're going to augment the action space. So already we've augmented the state space by adding the little v in there, but now the action space will also be a whole vector, which includes both the original action that the agent should take to interact with the world, but it'll also include these future vectors or future value demands in vector form. And so if we want to guarantee our expected reward at the current step is at least v, well, we have to satisfy this equation here, which is basically the standard policy evaluation equation. So this just says our current reward plus our expected future reward is at least the value. So if we can choose little v satisfying that, then we're good. We're guaranteed that our total value will be at least v. All right, so now if we do all of this, this is the new problem we need to solve. And this is specifically for expectation constraints, just to give you an idea. So if we want to minimize our total expected cost while satisfying our values at least v, then this is the total problem we need to solve. And then finally, our optimal value will exactly be the largest v that ensures our total cost is at most capital B, our budget. So what's the problem here? So I've already augmented the state space with potentially an infinite number of additional variables. That's not great, but we can deal with that just by rounding, like in the original knapsack problem. The bigger issue is that we have too many actions now. So remember, we have to remember or keep track of the future value for every state in our action space. So that's going to immediately give us an exponential number of actions. Even if you only had two values, let's say the value options were 0 or 1, well, that's 0 or 1 demand per state. So you're getting a total space of exponentially large actions. But the way we're going to deal with that is by using that space recursion thing I mentioned before. So what are we going to do? Well, just notice this equation. This is just the reward, the expected value, the reward plus the future values. Well, notice that these things don't really interact, right? You can choose the V1 separately from the V2 from the et cetera, et cetera. So why don't we just do recursion to pick each of the V's in order? So we could start by choosing VS and then go backward in time, or I guess technically backward in space, and choose the VS minus 1, use that information to keep propagating back to the future. So if we do that, we get this equation here. Note here, little u is the partial sum. So this is, say, like v1 plus v2 plus up to vt minus 1. And then we're going to use that in order to compute the cost, which we assume could be broken down recursively, right? So that's just the recursion equation in the minimum. So I wouldn't worry too much about, there's a g there and some random variables, but the important thing is that we can recursively break this down and choose each of the VIs independently. And this saves us from having to consider an exponential space of these, because now we can just pick each one sequentially. I like to think of this as we just have another sequential decision-making problem now over the V space. So we're basically doing two RLs, a nested RL and then overarching RL. And then at the very end, once you've chosen all your V's, the little u will just represent your total value. So then we can just check, okay, was our total value at least the budget or not? And that's how we finish off the DP there. So now for the approximation part, we're just going to do like a standard rounding, nothing too complicated. So here I'm just going to tell you about the relative approximation. I just think that's probably more interesting to at least the theory audience, but the additive one's almost identical. So the idea here is we're just going to round each value down to some uh, multiple of something or some um, exponent of something. So here we're just doing the closest one in the set of powers of 1 over 1 minus delta, where we're going to choose delta in a second. Now, the important thing here is because we're rounding values, not just immediate rewards like you would do in the knapsack problem, you're going to accumulate a lot of error. So the main dynamic programming is going to accumulate error over time. And then the sub-DP algorithm, which is the one we just created to pick the V's, that one gives you error over space. So overall, if you just did this rounding, what you're going to guarantee is that your total expected value will be at least this fraction of the demand raised to the SH power. So that's from state, space error, and time error. That's where the SH is coming from. So if you did the normal rounding approach in RL, you would just get the H there. You wouldn't get the additional S. So now we can just choose this delta epsilon over SH, and that guarantees us a 1 minus epsilon approximation to the optimal value. So that's the key approximation part. So now, technically, we have to use a different rounding per time step H due to a subtlety in how this works. So like I said before, in the original knapsack rounding approach, you're basically doing a rounding in a pre-processing step. So you're just rounding all of the V's and then inputting it into the algorithm, and you don't care anymore. It's just the normal knapsack. But here, because of the fact that you have transition P's being multiplied by the future V, that's going to make it so whatever your initial pre-processing was, that will break you out. So whatever your future values will end up being will no longer be of the same form as the originals. So because of that, we have to keep doing this rounding recursively to ensure we're always in that set of powers of 1 over 1 minus delta. This isn't, something that's it's not really causing a lot of technical problems, but it is something I wanted to mention because it's kind of it's not really standard, I'd say, for RL applications. But that concludes basically the main ingredients of the algorithm. So there's those 3 key steps. We're going to augment the states with the value demand. Then we're going to solve the demand problem by augmenting the action space with also value demands. And then we can solve that Bellman equation with exponential vectors by doing another dp over the V's. And those are the key ingredients to the algorithm. So finally, I want to tell you what we actually, what are the outcomes? What have we learned from doing all this? So specifically, the first theorem is if you want an additive approximation algorithm, all you need to do is guarantee me the reward range is bounded by a polynomial, which is not too crazy, and it's also the best you can do. If you relax that assumption, provably inapproximable. And if you want a relative approximation, all we need are the rewards to be non-negative. So it's a bit more relaxed. And like I said, these assumptions are necessary. So this is essentially the best you can do for the problem. So in conclusion, I want to point out that this actually addresses a pretty famous open problem from the constrained RL world, which is there exists a polynomial time approximation algorithm for almost sure constraints, anytime constraints, and then deterministic expectation constrained policies. And this last one has been an open problem for, I think now it's been 25 years actually. So the first two, the almost sure and anytime constraints, those are very new problems in the past like 2 years, I'd say. But this deterministic policies problem, just for classical expectation constraints, basically it was proven it was NP hard 25 years ago, and since then, no one has touched the problem other than through exponential time mixed integer linear programs. So this is actually the first polynomial time solution for that problem. Great. And so I guess just a quick little some future work if anyone's interested. This all is just for one constraint. So we do have these powerful algorithms, but just for one constraint isn't great. Like it's definitely better than nothing. But are multiple constraint problems really much harder? So, are there special cases where they're solvable? Maybe the smooth complexity is better. This has all been about worst case complexity. I don't know. I'm not totally sure. I have a follow-up work that addresses this a little more, but it's still a huge open question that I think is really important. And with that, I will thank you all for attending. And this is the QR code to the paper if anyone wanted to check it out. And I'm happy to take questions.
Hey, thank you so much. That was very, very good. And I'll be honest, I sometimes get lost in theory talks, but that was very approachable.
Glad to
Um,
hear it.
if anyone has any questions, feel free to unmute and shout them out, or if you type in the chat, I can read them out.